This video covers Part 1 of Section 3.2, Proving Existential Statements. Many statements of both definitions and theorems in advanced mathematics involve the existential quantifier. In order to show that a particular mathematical object satisfies such a definition, or to prove such a theorem, we need to be able to show that an existential statement is true. According to the definition, an existentially quantified statement, there exists an x such that p of x is true, provided that there exists at least one element x in the domain, an example for which p of x is true. We'll start with some definitions concerning numbers that involve the existential quantifier. An integer n is even, provided that n equals 2k for some integer k. An integer n is odd, provided that n equals 2k plus 1 for some integer k. In symbolic form, n is even, provided that there exists a k in z such that n equals 2k, and n is odd, provided that there exists a k in z such that n is equal to 2k plus 1. For our first example, we want to verify the following results concerning even and odd integers. First, we want to show that negative 294 is even. While this might seem obvious, since this ends in 4, we know that negative 294 is even. What we want to do in this example is to prove this using the definition. According to the definition, to show negative 294 is even, we need to show the existential statement shown there is true. That is, we need to show there exists an integer k such that negative 294 equals 2k. Now, to prove this existential statement is true, we need to find an example. So solving this propositional function for k, we see that we should choose k is equal to negative 147. And since k equals negative 147 is an integer and satisfies the propositional function, negative 294 equals 2 times negative 147, this proves the existential statement is true, and thus negative 294 is even. Next, let's look at showing 307 is odd. According to the definition, to show 307 is odd, we need to show there exists a k in z such that 307 is equal to 2k plus 1. So to prove this is true, again we need to find an example. Solving the propositional function for k, we see that we should choose for our example k is equal to 153. Since k equals 153 is an integer and satisfies the propositional function 307 equals 2 times 153 plus 1, this proves the existential statement is true, and thus 307 is odd. Finally, we want to show that 0 is even. Now, this may or may not seem obvious, but it is certainly a question with a lot of websites, over 250 million hits on Google, devoted to it. We'll show that 0 is in fact even according to our definitions. To show 0 is even, we need to show there exists a k in z such that 0 is equal to 2k. So we choose k equals 0, and since k equals 0 is an integer and satisfies the propositional function 0 equals 2 times 0, this proves the existential statement, and thus 0 is even. For our next definition, a real number r is rational provided that there exist integers p and q with q not equal to 0 such that r is equal to p over q. In symbolic form, r is rational provided that there exists a p, there exists a q not equal to 0 such that r is equal to p over q, where the domain for p is the set of integers and the domain for q is the set of non-zero integers. A real number r is irrational provided that it is not rational. So for an example, we want to show that 17 is rational. To show that 17 is rational, according to the definition, we need to show there exists a p, there exists a q not equal to 0, such that 17 is equal to p over q, and both p and q are integers. Now there are various possible choices for p and q. For instance, we can choose p is equal to 34 and q is equal to 2. Then p equal 34 and q equal 2 are integers, with q equal 2 not equal to 0. And 17 is equal to 34 over 2. This proves the existential statement, and thus 17 is rational. Next, we want to discuss constructive proofs of existence. There are two methods of proving an existential statement. The first method is called a constructive proof of existence. In such a proof, we either explicitly find an example x in the domain D, for which the propositional function p of x is true, or we give a set of directions for finding such an x. After finding an example, we then need to verify that it is indeed an example, meaning that it belongs to the appropriate domain and satisfies the propositional function. There are then two parts to a constructive proof of existence: finding the example and then verifying that it satisfies the necessary conditions. This was the procedure used in each of the above examples. In each case, we explicitly found an example for the existential statement. We then verified, or at least stated, that our example belonged to the appropriate domain and satisfied the propositional function. This is the procedure for proving an existential statement of the form there exists an x in D such that p of x, using a constructive proof of existence. Our first step is to find an example x. So first we need to either explicitly find an example x or provide directions how to obtain such an example for which p of x is true. Now we may obtain the example by guessing or construction using information deduced from the propositional function p of x. We often work backwards from the propositional function p of x. Alternatively, we may devise a procedure or an algorithm that will produce such an example. And you'll see how this works as we go through some of the examples. Our second step is to verify that x satisfies the required conditions. So after finding the example, we must then verify that it is indeed an example for the existential statement. To show this, we need to show that it satisfies the two conditions. The first is the domain x must belong to the appropriate domain D. And second, the propositional function p of x. So we need to show that our example satisfies the propositional function. Now very often this verification, or parts of it, will be carried out as part of the construction of the example. However, it is still important to remember that both parts, construction of an example and verification, are required when writing up the proof. When we work backwards from the propositional function to find an example, we can often retrace our steps in reverse order for the verification. This will be illustrated in our subsequent examples. To emphasize the two parts of a constructive proof of existence, it's helpful to write the proofs using two columns, where in the left column we find the example, and in the right column we verify that the example satisfies the required conditions, namely the domain restriction and the propositional function. So for an example, we want to write out the two parts of a constructive proof of existence that a particular integer n is even. According to the definition, to show that n is even, we need to show there exists an integer k such that n is equal to 2k, or in symbolic form, there exists a k in z such that n equals 2k. So the two parts of a constructive proof are, we have our two columns. In the left-hand column, we're going to find our example k, and in the right-hand column, we're going to verify that our example k satisfies the two conditions. The domain, k must be an integer, and the propositional function, k must satisfy n equals 2k. For another example, we want to write out the two parts of a constructive proof of existence that a particular real number r is rational. To show that r is rational, we need to show there exist integers p and q, with q not equal to 0, such that r equals p over q, or in symbolic form, there exists a p, there exists a q not equal to 0, such that r equals p over q. So the two parts of a constructive proof are, again, we write down our two columns, and in our left-hand column, we're going to find our example, which in this case means finding a p and a q. In the right-hand column, we're going to verify that our examples, P and Q, satisfy the two conditions. The domain, P and Q are both supposed to be integers, and we have the additional requirement that Q is not equal to 0. And then the propositional function, P and Q must satisfy R equals P over Q. Now, while textbooks or the professors in your upper division courses may not write existence proofs using this format, their proofs will still contain the same information. Separating out the two parts of the proof in column serves as a reminder to complete both parts of the proof. Now, this format should not be confused with the two-column proofs that are typically used in high school geometry courses. There, the left column contains the steps in the proof, and the right column the reason for each step. We now consider an actual proof, albeit of a very simple result, illustrating this format. So for our example, we want to prove, for all integers m, 6m is even. First, write the statement to be proved in symbolic form. So this will be for all m and z, 6m is even. Now this is a universal statement, so we're going to use a proof by arbitrary element. So we'll start our proof by saying, suppose m is an arbitrary integer. We then need to show that 6m is even. To show this, we need to show, according to the definition, there exists an integer k such that 6m equals 2k, or in symbolic form, there exists a k and z such that 6m equals 2k. So now we have to prove an existential statement, so we'll start by setting up the two columns. So our two columns are, as shown, in the left column we need to find our example k, and in the right column we need to verify that k satisfies the two conditions. The domain, k is supposed to be an integer, and the propositional function, k must satisfy 6m equals 2k. So to find a k, we need an integer k satisfying the propositional function 6m equals 2k, and we can solve this for k, and we see that we need to choose k is equal to 3m. So now we've found our k. So we'll go over into the right-hand column, and since m and 3 are both integers, and the set of integers z is closed under multiplication, then we know that k equals 3m is an integer. And since k equals 3m, then we know that 2k equals 6m, so k satisfies the propositional function. So we've found our example k, and then we verified that our example satisfies our domain requirement and our propositional function. So this proves the existential statement, there exists a k and z such that 6m equals 2k, therefore 6m is even. And since m was assumed to be an arbitrary integer, this proves the universal statement, for all m and z, 6m is even. Before proceeding with another example, let's just discuss a little bit the process of starting a proof. Now, while there is no algorithm that will enable you to prove any mathematical result, there are some steps you can follow to get almost any proof started. The first step is, as mentioned several times already, is to write the statement to be proved in symbolic form. So the symbolic form of the statement will determine the method of proof to be attempted. And as part of writing the statement in symbolic form, you should identify the domain of each variable. Our second step is to specify the variables and state the hypotheses. So you want to identify the variables you will be using in the proof. For instance, if the statement to be proved involves a universal quantifier, you will typically begin the proof by a statement like, suppose n is an arbitrary integer, or let x be an arbitrary real number. Next, you want to state the hypotheses. These will be the facts you're going to be assuming about the variable. For instance, you may be assuming that n is odd or that x is positive. Third, you want to state the conclusion. In order to construct a proof, you need to know where you're headed, or at least where you want to go. So you should state what you need to show at each point of a proof. Be careful, however, not to confuse what you're supposing, a hypothesis, and what you need to show, the conclusion. For this reason, it's important to always preface a conclusion by including the phrase, "we need to show." If you just write down a conclusion without specifically indicating that it's a conclusion, it's easy to get confused and to start using it as a hypothesis. Fourth, you want to restate the conclusion using an appropriate definition. In a typical proof, the desired conclusion will involve one or more definitions. For instance, in the example above, we needed to prove 6m is even, so we referred to the definition of an even integer and restated the required conclusion using that definition. After restating the conclusion using a definition, you will typically be faced with another quantified statement. To prove this statement, you may have to repeat steps 1, 2, and 3, so there may be a proof nested inside the main proof. You may in fact follow these steps through several iterations in the body of your proof. So for our next example, we want to prove something a little bit more complicated. The square of any odd integer is odd. We need to write this statement in symbolic form. Before doing this, we first rewrite the statement formally using a variable as, for all odd integers n squared is odd. This has symbolic form for all n squared is odd, where the domain for n is the set of odd integers. This is a universal statement, so we start with a proof by arbitrary element. So we suppose n is an arbitrary odd integer. We then need to show that n squared is odd. To show this, we refer to our definition. So we need to show there exists an integer k such that n squared equals 2k plus 1. Now we need to prove this existential statement. So we'll start by setting up the two columns. In the left-hand column, we need to find our example k. In the right-hand column, we need to verify that k satisfies the two conditions. The domain, k is supposed to be an integer, and the propositional function, n squared equals 2k plus 1. So to find our k, since we're supposing n is an odd integer, then there exists an integer L such that n equals 2L plus 1. This implies, by squaring both sides, that n squared equals 2L plus 1 squared, which expands to 4L squared plus 4L plus 1. Now we need to find a k such that n squared equals 2k plus 1. If we rewrite the above expression for n squared as 2 times the quantity 2L squared plus 2L plus 1, from this expression we see that we should choose k to be 2L squared plus 2L. So we've now found our example k, and so we're ready to go over into the right-hand column and verify our two conditions. For the domain, we can say that since L is an integer and Z is closed under multiplication and addition, then our k equal 2L squared plus 2L is going to be an integer. For the propositional function, we can refer to the work on the left, which shows that n squared equals 2 times the quantity 2L squared plus 2L plus 1, which is equal to 2k plus 1, since we chose k to be 2L squared plus 2L, the quantity in the parentheses. So k satisfies the propositional function. So we found our example k, and then we verified that our k satisfies our two conditions. So this proves the existential statement, there exists a k in z such that n squared equals 2k plus 1, and therefore n squared is odd. And since we supposed n was an arbitrary odd integer, this proves the universal statement for all n squared is odd. Note that the proof in the preceding example starts by focusing on the conclusion, or what needs to be shown, namely that n squared is odd, instead of starting with the hypothesis. The next step was to restate what needs to be shown in order to show this conclusion, namely there exists an integer k such that n squared equals 2k plus 1. This followed from the definition of an odd integer. It is only at this point of the proof, when proving the existence of such an integer k, that we go back to the hypothesis, that n is an odd integer. In general, it's a good idea in constructing any proof to focus first on the desired conclusion. Ask yourself what needs to be shown in order to show the conclusion. At this point, look at your assumptions or suppositions and other facts which you know. Now, the proof given in the preceding example obviously includes quite a bit of discussion along the way. A typical proof of this statement in a textbook may be considerably shorter, along the lines of the following. Suppose n is an arbitrary odd integer. Then there exists an integer L such that n is equal to 2L plus 1, which implies n squared equals 2L plus 1 quantity squared, which is 4L squared plus 4L plus 1, which is 2 times the quantity 2L squared plus 2L plus 1, which can be written as 2K plus 1, where K equals 2L squared plus 2L is an integer, and thus n squared is odd. Now, this is certainly an acceptable proof, and once you've gained more experience in writing proofs, you'll probably be writing proofs in a format similar to this. In this course, however, your goal is to learn how to write proofs, and it's helpful to write out more detail and to follow the guidelines for writing proofs contained in this section and in the previous section. As one final comment about the preceding example, note that the statement could also be written in the equivalent symbolic form for all n in Z. N is odd implies n squared is odd, where the domain is the set Z of all integers rather than just the set of odd integers. In this case, we would start the proof by supposing n is an arbitrary integer. We then need to show that the conditional propositional function n is odd implies n squared is odd is true. We'll be discussing methods of proof for conditional statements in detail in a later section. The fundamental method is a direct proof where we suppose the hypothesis n is odd. We then need to show the conclusion n squared is odd. The proof from this stage will then be identical to the above proof in the example. For our next example, we want to prove that the sum of any two rational numbers is rational. We need to rewrite the statement in symbolic form. Before doing this, we first rewrite the statement formally using variables as, for all rational numbers r and s, their sum r plus s is rational. This has symbolic form for all r in Q, for all s in Q, r plus s is in Q, where the domain for r and s is the set Q of rational numbers. Now, this is a universal statement, so we use a proof by arbitrary element. So we'll start by supposing r and s are arbitrary rational numbers. We then need to show that r plus s is a rational number. To show this, we need to show there exist integers p and q with q not equal to 0, such that r plus s equals p over q. Or in symbolic form, there exists the p, there exists the q not equal to 0, such that r plus s equals p over q. Now we need to prove this existential statement, so we'll start by setting up the two columns. In the left-hand column, we need to find our example, which in this case is to find a p and a q. And in the right-hand column, we need to verify that our example satisfies the two conditions. The domain, p and q are both integers, and q is not equal to 0, and the propositional function, r plus s equals p over q. Now, our hypotheses are that r and s are both rational. Since r is rational, then there exist integers a and b with b not equal to 0, such that r equals a over b. And since s is rational, then there exists integers c and d with d not equal to 0, such that s is equal to c over d. Then their sum, r plus s, equals a over b plus c over d. Rewriting these fractions over a common denominator, we obtain r plus s is AD over BD plus BC over BD, which is equal to AD plus BC over BD. This tells us to choose P is AD plus BC and Q is BD. So now we've found our example for P and Q, so we're ready to go over into the right-hand column. And for our domain, we can say that since A, B, C, and D are integers, and Z is closed under addition and multiplication, then both P equal AD plus BC and Q equal BD are in Z. Also, since B is not equal to 0 and D is not equal to 0, then Q equals BD is not equal to 0. So this verifies our domain condition. For our propositional function, we can refer to the work on the left. So the work on the left shows that R plus S equals AD plus BC over BD, which is our P over Q. So P and Q satisfy the propositional function. So we found our example. We verified that our example satisfies the two conditions. And so this proves the existential statement. And this tells us that R plus S is rational. And since we supposed R and S were arbitrary rational numbers, this proves the universal statement. We're going to close the video by discussing very briefly disproving existential statements. According to the definition, an existential statement, there exists an x such that p of x is false, provided that the propositional function p of x is false for all x in the domain. Or equivalently, provided that its negation, not there exists an x such that p of x, which is equivalent to for all x not p of x, is true. So disproving an existential statement is equivalent to proving a universal statement with the propositional function negated. And so any of the methods used for proving universal statements can be applied to disprove an existential statement.